All right, so let's compute the moment generating function and cumulant generating function for some common distributions. See how this works. So some examples. Okay, so first let's start with x, Poisson parameter lambda. So then in this case, moment generating function of x, some e to the tk times the mass function e to the minus lambda over k factorial, lambda to the k e to the minus lambda over k factorial. How do we calculate this? Well, what we realize here is e to the tk lambda to the k, so we get lambda e to the t k. Now e to the t is positive, right? So and then we have lambda e to the tk. E to the t is positive, right? So e to the minus lambda can come outside because it's a constant. And now what we realize is, okay, we have this is like the key piece of a Poisson variable with parameter lambda e to the t. So we have to multiply and divide by it. And then, of course, divided by k factorial. So this piece now is the mass function of Poisson with intensity lambda e to the t. So it sums to 1. So this is now just equal to e to the minus lambda plus e to the t. Cumulant generating function of x is the log. Log of an exponential is very easy to deal with. Minus lambda plus lambda e to the t. And the derivative, right? The kth derivative of the cumulant function is just lambda e to the t for all k bigger than or equal to 1. So all cumulants then, so then this tells us that all of the cumulants of a Poisson are the same. They're all lambda. Next, let's consider the binomial distribution. So let's let n be binomial n and p. Q is 1 minus p. Moment generating function by definition, sum from k equals 0 to n. N choose k. Well, let's do, it's going to be e to the tk. N choose k. P to the k. Q to the 1 minus, q to the n minus k. The e to the t k can get absorbed in with p, and so we have n choose k, p e to the t k, q to the n minus k. But this is just the binomial, this is just a binomial formula with x, this is equal to x plus y to the n with x equal to p e to the t and q equal to y. So we get p e to the t plus q to the power n. Cumulant generating function, which is the log of the moment generating function, is n times the log p e to the t plus q. First derivative of the cumulant generating function here is n times 1 minus q over p e to the t plus q. Second derivative is npq e to the t over p e to the t plus q squared. And together, these both inform us that expectation of x, which is the first cumulant evaluated at 0, is n times p. And the variance of x, which we've seen is the second cumulant evaluated at 0, is npq. For a third example, let's let x be gamma with parameter r lambda. So in this case, moment generating function, expectation e to the tx, e to the tx, lambda to the r, x to the r minus 1, e to the minus lambda x dx over the gamma function. Rewriting this now, we can fold the exponential in, and we see that lambda, this is lambda to the r, x to the r minus 1, e to the minus x lambda minus t over gamma r. And so we see that this is like the gamma function with parameter lambda minus t instead of lambda. So we take the lambda to the r out, and then we can add a lambda to the r in by dividing out, right? X to the r minus 1, e to the minus x lambda minus t divided by gamma of r. This is now the density of a gamma r lambda minus t. And so this is equal to lambda over lambda minus t to the r, provided that lambda is greater than t, or t is less than lambda. Otherwise, this is going to be infinite. For valid values of t, though, t less than lambda, the cumulant generating function is r times the quantity log of lambda minus log of lambda minus t. First derivative with respect to t, we easily calculate it's r divided by lambda minus t. Second derivative is r divided by lambda minus t squared. And this gives us then that the expectation of x, as we already have calculated otherwise, is r over lambda. The variance of x is r over lambda squared. And then finally, for our examples, let's let z be standard normal. Then in this case, the moment generating function, expectation e to the tz, times the density e to the minus z squared over 2 dz. Now to calculate this, one thing that we have to do is we're gonna actually complete the square. So we're gonna actually, so one thing we can do is we can add, so we're gonna add and or multiply and divide. So we multiply by e to the t squared over 2. And then what we're left with here is, what happens is we get, when we pull everything together, we end up with an exponent which has, it's the density of a normal with variance 1, but with mean t. So this integrates to 1, and the moment generating function comes out as just e to the t squared over 2. Now, if x is normal with mean mu and variance sigma squared, then we can actually write, so this gives us a way to compute the moment generating function directly of an arbitrary normal 0, 1 by realizing this relationship, right? So z is x minus mu over sigma, right? So this is a relationship between normal 0, 1 and normal mu sigma squared. And so in this case, I'm sorry, this should be mz of t. Mx of t is defined as the expectation, and we can actually write it as expectation of t times sigma z plus mu, right? So, but this is expectation of e to the sigma t z times e to the t mu. E to the t mu is just a constant, so that can come outside the expectation. And then what we're left with here, this is the evaluation of the moment generating function of z evaluated at sigma t. Right, so this is e to the t mu, e to the sigma t squared over 2. And so we usually just write this as t mu plus sigma squared t squared over 2. Okay. So then in this case, the cumulant generating function of a normal with mean mu variance sigma squared is just the log of an exponential. So it's t mu plus sigma squared t squared over 2. The first derivative is mu plus sigma squared t. The second derivative is sigma squared. And what's interesting about this is that all higher order derivatives bigger than or equal to 3 are all 0. So the cumulants of all of the higher order cumulants of the normal distribution are all 0. And the we see that the moments come out very easily here. If we evaluate this first derivative at 0, we easily get mu. Second derivative at 0 is just the constant sigma squared. So here we've seen how we can actually, you might be surprised that we can actually calculate the moment generating function pretty easily for a lot of distributions because of the nice properties we have of these densities. And it turns out that this trick of making a density inside, when we're trying to integrate something, we try to make manipulate it so that it looks like the density of a known distribution. This is a very powerful trick that allows us to get closed form solutions to these functions.